Hello, my name is Jana, and as part of this 2022 cohort, I worked on efficient architectures to solve dense video understanding tasks. We called our project Treating Video as an Image. But what exactly are dense video understanding tasks? Given a video, dense video understanding tasks always try to get per pixel labels for this task. For example, here, we try to know which pixels belong to cars and color them blue, and which pixels belong to trees and color them green. If you look at autonomous driving or augmented reality, it becomes pretty clear why we often have to solve these tasks within harsh memory or time requirements. Now, there are solutions to these tasks out there. For example, this is the master firmware architecture, which extracts features from the frames using a backbone. A pixel decoder then blows up those features again and hands them to the transformer decoder. The transformer decoder, in return, extracts a feature per object, which are dot product with the per frame features to get the video instant segmentation mask. So the transformer decoder relies on dense per frame features from the pixel decoder. Now, master firmware, like a lot of state-of-the-art video transformers, was actually never built to work on video. It was mainly constructed to work on images. This is why a huge majority of master firmware is actually run on a frame-by-frame basis. Only the shared transformer decoder incorporates some form of context and adapts the architecture to be capable to actually work on videos. But this introduces a lot of overhead. Even with a relatively simple R50 backbone, roughly 70% of the processing time go towards this frame-by-frame processing. We thought that this introduces a lot of unnecessary overhead, because frames are not totally unrelated images. Instead, they're highly correlated, so they actually should share a huge amount of features in between each other, and it seems unnecessary to run the backbone and the pixel decoder separately for each single frame. So we instead propose that you may merge the original frames during the first convolution, run the backbone and pixel decoder only once per frame is merged. Afterwards, we add a video expansion layer, which takes the output of the pixel decoder and expands them back to per frame features. Those dense per frame features can then be used by the transformer decoder to create segmentation masks. This means Treating Video as an Image can learn itself what features it wants to keep between each frames and what features should be shared among the frames. All in all, as you can see here, we get close to perfect speedup for the backbone and the pixel decoder. If we merge two frames, we only have to run the backbone and the pixel decoder 1/2 of the time, and if we merge 5 frames, the total compute time for the backbone and the pixel decoder is only 1/5 of the time. But of course, we also added the merging step and the video expansion, which we also have a look at. But as you can see here, the overhead we added for the expansion and the merging step are only minor, and the overall speedup that we gain through the pixel decoder and the backbone are so enormous that the newly introduced overhead is only minor in comparison. Next up, we try to train our model. We first tried to train our model on the YouTube Viz 2019 dataset with mask loss, so with the loss that is applied after the transformer decoder. But this yielded poor performance, and we hypothesized that this is because we had too little data. Because YouTube Viz 2019 only contains 2,000 clips from around 500 unique scenes. And we thought 500 unique scenes is probably not enough to train an architecture what features are actually important between frames and what features can be shared. That is why we currently try to train our model on the outputted features of the default architecture, so the features that are outputted by the pixel decoder. This way we can learn in a student teaching manner, and we actually can learn on unlabeled videos. Future work, of course, states that we want to try to evaluate our method on the validation set and compare this against an interpolation-based pixel-wise nearest neighbor baseline. We are also motivated to have a look at the memory accuracy trade-off. All in all, frame-by-frame processing introduces a lot of overhead, which we believe is not necessary. Treating video as an image has the potential to significantly improve latency with only minor drops in accuracy. Last but not least, I'd like to thank my supervisors, Dave Ramanan and Jonathan Luiten, as well as Rachel Burton and John Dolan, who made this RIS experience possible, and my sponsors, the Argo Eye Center for Autonomous Vehicle Research and the German Academic Exchange Service.